Okay, folks, this is chapter 26. This is the non-example parts of the slides, in case you missed it or want to fall asleep again or something like that. Anyway, so let's do this thing. This is the first examples as using finite state machines as controllers. It's kind of presented in the context of counters and a bunch of example problems. Experiment 12 also, and I'll go over that, but I will skip over the example problems. So we're moving towards using finite state machines as controllers. So this is your finite state machine here. You got these external outputs, which are going to be used to control stuff. You've got these external inputs, which is essentially status inputs from your circuit. So the way this is going to control things, it's going to read the status inputs, decide what to do, send out the appropriate control inputs to do what you wanted your circuit to do. So I showed you this on the first day. That probably didn't make much sense, but we have these circuits which are controlled. I call them controlled circuits. So essentially, these circuits, which is everything we've had so far, except for the state machines, you got data coming in, data coming out. You got control. You can typically control these with inputs, and the circuit generally gives you some type of status output. Okay, and so what this is going to do is going to be, we're going to use some type of controller circuit. In our case, we're going to use a finite state machine. It's going to read the status inputs, kick out the appropriate control to do what you designed the state machine to do. Okay, and so this is all the modules we've worked with so far. So going over these real quick, we got a status output on the ripple carry adder. We got control inputs on the decoders. We've got control inputs on the muxes. Oh, this thing works. We got status outputs. Oh, it's off. Okay. We got status outputs on the comparator, status outputs on the parity generator, and the register here. We don't have any status outputs, but we do have a bunch of control inputs, which is clear and a load and a clock. So we're going to talk about counters today. A counter is a type of register. Here's your Venn diagram. A whole bunch of different types of counters out there. We are going to use one type of counter, which is this binary counter. Certainly, if you're really into it, you could look up these other counters. All we're really interested in is binary counters. Next time, we'll talk about shift registers and how cool they are, but today it's just counters. Okay, so counters. This is the basic lingo associated with counters. I've got a counter has typically a count sequence. For us, we've been designing these specialty counters primarily, but for now on, generally the counters count up and count down, as you'll see in a bit here. These are referred to as n-bit counters, which means n can be any number, probably not 0, probably not 1, anything greater than that. Typically, if you want an 8-bit counter, it's an 8-bit counter, not an n-bit counter. Now, typically, these counters count up by incrementing. They count down by decrementing, or they can count up and down based on the control inputs. They can typically also hold values, which means not count up or count down. It just keeps the same state. These counters are typically circular without putting a lot of effort into it, so they overflow. So it overflows from all ones output of the counter to all zeros. It happens naturally. It underflows if you're counting down from all zeros to all ones, referred to as circular. Once again, you don't really have to design that into your counters. It happens naturally. Typically speaking, these you can load new values into these counters to start to count at any value you want, which I refer to as parallel load. And typically, if you want a 16-bit counter, it's really easy to make a 16-bit counter out of two 8-bit counters, which is referred to as, generally speaking, these are cascadable. Here's my super generic counter foundation module diagram. As you can see, it has data coming in and data coming out. It typically has a status output. Status output is ripple carry out. This ripple carry out indicates when it's at its terminal count. And what you'll see here, this terminal count is depending upon the direction. So if you're counting up, the terminal count is all ones. If you're counting down, the terminal count is all zeros. Okay, so typically speaking, here's every possible input you can see over here. Clear, load, up, down, hold. Okay, and typically when you design a counter or work with counters, you're not going to use all these. I just threw them in there just so you could get a good feel for what's happening with these. And I'll go over a few examples in a second here of how you specify these counters in your design. Okay, remember this is the FSM down here. The outputs of this FSM are control signals. It's going to be connected, generally speaking, to these control inputs on the counter. The status output of the counter is going to be an external input to the state machine. Well, this is an example, a timing diagram example. I don't have this in draw mode, or else we could actually do this. Maybe I could put it in draw mode. Okay, and maybe not, but escape, and escape, and draw mode, insert, draw. I thought there was a draw mode. Animations, file. I'm not seeing it here, so we're gonna skip the draw mode here. Slideshow from beginning, and here we are. Well, here's the solution to it. Like I said, if I could draw this by hand, I would do that, but I don't have that ability. What we're going to do here is, generally speaking, when I need a counter, I'm not going to design it from scratch. Counters generally all do the same thing. I'm going to go grab a module and use it as I need to. So this is a Verilog model of a generic in-bit counter. It has but by the way the code is drawn, it has an asynchronous clear here. You can see that the clear is the first value in this process here. So this process, because I use the pause edge and a neg edge, it's going to induce a sequential circuit, which is what I want. Counter is a type of register, but the fact that clear comes first is in fact that makes it a asynchronous counter. It's not waiting for the clock edge. Okay, so all the other inputs are sensitive to the clock edge. So the issue here is, by the way it's written, I have a load, an up, and a down. This happens to be an up-down counter. The problem with this counter is it has no load input, and so it's sort of an issue. I actually already uploaded a new counter to the website, which essentially what I did is I removed that last else if here. So by the way this is written, clear has precedence over load, load has precedence over up. But you can see here, it's up equals 1. If up equals 1, it increments. If up equals 0, it decrements. And that's essentially my entire counter here. Remember, if the load is asserted, it takes that D input and loads it into the counter. This counter also has a RCO on it. This is a direction-dependent RCO. Once again, it's RCO. If you're counting up, RCO turns on when the output is all ones. If you're counting down, the RCO turns on when the output is all zeros. So this is necessarily a combinatorial circuit. It's just based on these two inputs here, which is up and count. And notice for the sequential circuit, I am using the non-blocking statements. For the combinatorial circuits, I'm using blocking statements, which I'm always going to do. One other thing to note in this thing is I'm using a replication operator. So this AND count and this OR count here essentially says this ANDs all the bits together in this thing, and it says if they're all 1, that's the positive condition I'm looking for. So if it's counting up, AND. all the bits are 1, that's what this says, it's going to turn that RCO on. Or if it's counting down and all the bits are 0, that's what this little thing here says with this replication operator. It also turns the RCO on. Otherwise, it turns RCO off. Okay, so once again, it's a combinatorial circuit. I have if, I have a catch-all with this final else down here. It's going to be a decent looking circuit. It's actually going to work. So last slide here. These are the counters. Whenever I need a counter, I just plop it down here, and I usually have to say something about it. So the issue here is for this counter in the upper left corner there. I don't really have to say anything about it because it's essentially an up counter. And same with this up counter here in the upper right. It does have an RCO, a little bit of difference there. But if you look at this, the middle row on the right side, you can see it has a hold input and an up input. So it's not clear from these inputs which one has precedence. So if I were to use this counter, I would have to say what has precedence, hold or up. I'd also have to say it's generally accepted that when up is a 1, it counts up, but it's not really clear from the diagram what happens when up is a 0. I have to state. So it's either going to be, typically it's either going to be counts down or it holds. But I would not know by looking at the diagram. So anytime you use any of these diagrams, you have to list the precedence of the inputs, and you have to list all possible combinations of inputs. So generally speaking, something like a hold, if it's asserted, it holds. If it's not asserted, it doesn't hold, etc., etc. But typically in the ups, sometimes they count down when the up is not asserted. You don't really see too many circuits with both an up and down input like you do in the lower right here. But in this case, by all means, if you did it right, you'd have to specify what the circuit's doing when both up and down are asserted. And you certainly have to give it precedence on these things too. So whatever you do in your diagrams, you can use whatever you want, but you have to be very clear about exactly what it's doing. Okay, and that's it, folks. That's all I have for these design problems. And